So now you know about two types of losses. So the first one was the cable attenuation, the second one was the path loss. And you know the one gain value, the antenna gain. And I promised you that we use these values in systems engineering, and now we see how. You in a communication system, you have a transmitter, and the transmitter generates a signal, a modulated signal carrying the information with a certain power, let's say 40 dBm. And this is in linear scale how much? Yeah, it's 10 watts. And now we have a system. So here the transmitter contains all the things that we have already learned. It has a digital signal processing with coding, spectrum modulation, filtering, and so on, and an RF front end with a mixer and amplifiers and filters too, and more amplifiers, and so on. And this is, we have already learned about these things, and now we take into account that there's a feeding cable to an antenna. The antenna has a gain of 22 dBi in reference to an isotropic antenna. Remember the I here. And the feeding cable has a loss of 2 dB. On the receiver side, we have an antenna with less gain. It just has 11 dBi, and the cable is shorter, so it has only 1 dB loss. And here we can assume a free space path loss model, and the path loss here is 140 dB. Yeah, it's very high compared to the losses in the cables, but the cable losses cannot be neglected here. And now the question is, how much power is received here? So we know the transmission power, we all know all the system parameters here of cables, antennas, and the transmission channel. Yeah, so remember that this one here is the first transmission channel, then there's a media conversion, the second transmission channel, media conversion again, and then here the third transmission channel. So now the sum of the gains is sum of two antenna gains, 33 decibel. Okay, and I forgot this one here. So here, if you refer to the values of the antennas, it is important to denote the I. Here, when you talk about the sums, it's not so important. But here I would recommend to always write the I, so that you know that this refers to an antenna gain, which is referenced to an isotropic antenna, because antenna gains can also be referenced to other references. To show, to indicate the reference, always write an I here. And here the sum of the losses, it's the two cable losses and the path loss, and in sum they sum up to 143 decibel. And now you can calculate the received power in dBm, and the transmitted power is 40 dBm plus the gains of the antennas minus the losses, and we get minus 70 dBm here at the receiver. So you see that you have a total attenuation of the transmitted signal to the received signal by by 110 decibel. You might think that this is very much. It is, but these are typical values for a real communication scenario. So this is not uncommon. This is a typical value. So here you again see the advantages of using decibel, because you can just create some indifferences instead of multiplying numbers which with so very large or very tiny numbers, which can be a bit complicated. So now you know the received power here. This is good, but there's another purpose behind this. So in the last lectures you have learned about coding, modulation, spectrum, and I always told you that depending on the parameters chosen for coding, spectrum, multiple access and modulation, you have minimum signal to noise ratio requirements. So for example, if you have a spectrum with a long code sequence, then your signal is more immune against noise due to the processing gain which can be achieved. So you have more lax signal to noise ratio requirements, whereas if you use short code works or completely remove the spectrum, then you usually have very, very tight signal to noise ratio requirements. So this all have an impact on this requirement. But you know that the thermal noise floor is fixed at minus 173 dBm per hertz, and so you know that your noise floor is always fixed here, and you have a minimum requirement here, and your signal must be always above here. So if your signal is below this minimum requirement, then you probably won't be able to decode your signal, because if you violate this minimum signal to noise ratio requirement, then the bit error rate would be so high that no reliable communication is possible. So the keyword is coding. So the you always have to fulfill a minimum signal to noise ratio requirements to keep the bit error rate below a certain boundary, which is important for coding, so that the coding can detect and correct the errors. And because the thermal noise floor is fixed here, you have a minimum, so you have a requirement on the minimum power received here. So the received power must be always above this red dotted line. And again, an example about this topic. So you know, due to your coding and spectrum parameters, that you need a minimum reception power of minus 105 dBm. So you have total cable losses of 10 dB, you have antenna gains of 5 dBi in sum, and you have a transmission power of 20 dBm. The question is, how much is the maximum path loss which is admittable? And yeah, this is just some mathematics. So here it's the difference between the transmission power and the reception power plus the antenna gains minus the cable losses, and this gives a maximum free path loss of 120 dB. So the path loss must be below this 120 decibel. So we can say that the link budget is 120 decibel. So we know that a path loss of 0 dB would be okay, a path loss of 80 dB would be okay, still a path loss of 120 dB is okay, but 130 dB is not okay, because the received power will be lower than this minimum requirement. If it would be 130 dB, then the received power would be minus 115 dBm. Yeah, and so we can say that link budget for our communication, so the budget for the link between the transmitter and the receiver is 100 decibel. And a practical use is given that the communication happens at a certain frequency, for example 868 megahertz, you can say how much is the maximum distance between the transmitter and the receiver, assuming free space path loss. So here this is the formula for the free space path loss, but modified in a way that we can calculate the maximum distance between them. So here you find the link budget, and here the this constant, the 32.4 dB, taken from the free space path loss model formula, and here it's here is the frequency and the reference 1 kilometer. And if you assume this frequency and this link budget, you see that the maximum distance between transmitter and receiver is 27.6 kilometers. So then last word. So you usually do not operate your communication at a point where the received signal hits the minimum signal power. So we are always above. So like before, this is the maximum distance, but it is of course always possible that the transmitter and receiver are closer together. For example, a distance of 10 kilometers would be fine. And if you have a distance of 10 kilometers, then the signal power is much stronger than the minimum requirement. And the difference between the current signal power and the minimum required signal power is the link margin. And so a greater link margin means less bit errors, and that you can change your modulation coding and spectrum parameters so that you can operate at a higher data rate sometimes. So for example, remember the orthogonal variable spreading factor code tree from chapter 7, which gave codes for the direct sequence spectrum. We used a variable spreading factor to change the data rate, at the drawback that a higher data rate has tighter constraints on the signal-to-noise ratio. And so if you have a good enough link margin, your communication system may decide that it changes the spreading factor of the direct sequence spectrum, but this would need another minimum signal power requirement here. But as you have enough link margin, this signal here still fulfills it, and you can achieve a higher data rate. Yeah, this can be one consequence. Not all communication systems have variable spreading factors and adaptive data rates, but many modern communication systems like Wi-Fi or 4G LTE do have adaptive data rate, which can adapt their data rate to the noise conditions in which the communication systems currently operate.